Hi. So today's lecture is about linear differential equation of order 1. Now we'll discuss linear differential equation of order n in general. Okay, so just let me tell you, so in general, an nth order linear ODE has the form an of x nth derivative plus an minus 1 of x n minus 1 derivative plus a1 of x y prime plus a0 of x y equal a function of x. We're going to discuss this in details in section 4.1. But the first order 1, it becomes what? a1 of x y prime plus a0 of x y equal f of x, or simply y prime plus p of x y equal q of x. Okay, these are the linear ODE of order 1 we discussed. It's y prime plus a function of x multiplied by y is equal to a function of y. Y prime can be multiplied by a function of x, and then you divide by it and you get this one. So this is the linear ODE of order 1. Now, in this case, on order n, if f is the function 0, if the right hand side is function 0, we say the ODE is linear homogeneous. Not to confuse, please, with Euler homogeneous. Fine? And just to tell you where I'm, this is section in the book, it's section 2.3. Okay? We're gonna do a little bit of 2.5 and a little bit of 3.1 along with the section, but I will tell you whenever I switch from section to a section. But all of the section will be about linear differential equation. Okay. So let's start with linear homogeneous of order 1. As an example, let's solve. So what's the form of linear homogeneous? Y prime plus p of x y. Now the right hand side is 0 if that equation is linear homogeneous. As an example, it's y prime minus x squared y equal to 0. How do I solve for the e? Now this is also separable. Notice, because you have y prime equal x squared y, so dy dx equal x squared, or you can solve it, I will tell you the other way, and then this is dy, so this is dy over y equal x squared dx, so log of absolute value of y equal x cubed over 3, plus a constant by integrating, and this is absolute value of y equal e to the x cubed over 3 plus c equal e to the c e to the x cubed over 3. So y is equal a e to the x cubed over 3. Fine. Let's add the condition y of 0 is equal to 1. Then you get y of 0 equal a e to the 0 equal to a. Same time is equal to 1. So this implies that a equal to 1. So y of x equal e to the x cubed over 3. Okay. Another way to do it is when you have y prime equal x squared y. It's really the same way, by the way. It is the same method, but here it was hidden. And then use that this is log of absolute value of y prime equal to x squared. Well, since y of 0 equal to 1, you can remove the absolute value, and then you integrate and use the antiderivative method. The antiderivative method is a special case of separable equation. So in general, this is how we solve. So in general, I have dy dx plus p of x y equal to 0. Then the way I solve it, it's dy dx equal minus p of x y. Then this is y prime over y equal minus p of x. And then and this is log of absolute value of y prime equal minus p of x. And then I integrate. Or we solve as separable. Okay? This is general method. So this is something like separable ODE. It's kind of straightforward. Okay. Now in general case, let's say I have linear equation, not homogeneous, okay, not necessarily homogeneous. For example, let's say I have x squared y prime plus 2xy equal to x. Now the goal is to transform the left-hand side of the ODE and make it and investigate if it's a derivative of some function. But notice that here I have x squared y prime, and here I have 2xy. X squared, the derivative of x squared is 2x. So using product rule, so from product rule, I have this is x squared y, the whole thing prime. Because what is the derivative of x squared y? It is x squared times the derivative of y plus the derivative of x squared, which is 2x times y. And now this is equal to x. Okay? And now I integrate, I use the antiderivative method, integrate, and you get x squared y is equal to x squared over 2 plus a constant. And this implies that my solution y of x is equal half plus c over x squared. And this is my solution. But here I was lucky that x squared, because the derivative of x squared was 2x. What if I have another example? What if I have y prime plus 2xy equal to x? Now here on the left hand side, I don't have the derivative of some function. I mean, this is 1 times y prime, and the derivative of 1 is 0. But notice that if I multiply the ODE by e to the x squared, I get e to the x squared y prime plus 2x e to the x squared y equal to x. Now notice that 2x e to the x squared is equal to e to the x squared, the whole thing prime. So this is e to the x squared y prime plus e to the x squared prime y equal x. I forgot to multiply the right hand side, equal x e to the x squared. But now by product rule, this is e to the x squared y, the whole thing, prime, equal x e to the x squared. And now you integrate, and you get e to the x squared y equal integral of x e to the x squared dx. But notice that this is u prime, I mean the derivative of x squared is 2x, so this is 2x half 2x. So this is e to the x squared y equal half e to the x squared plus a constant, and this implies that y equal half e to the x squared, y equal half plus c e to the minus x squared. So when I multiplied, so to begin with, the right hand side was not the derivative of some function. But when I multiply by e to the x squared, which is allowed, then I obtain the derivative. I obtain that the left-hand side is the derivative of e of some function. Okay, so we say that e to the x, that mu of x equal e to the x squared is an integrating factor to the ODE. Okay, so where does this e to the x squared came from? can I guess it? Well, let's see. So in general, I have y prime plus p of x y equal q of x. Now you need to, when you apply this method by multiplication by integrating factors, this is your ODE you have. I'm writing in the standard form y prime is multiplied by 1. And here I have p of x y equal q of x. So first I need to multiply. So there's nothing here. You need to multiply the ODE by an integrating factor mu of x such that the left hand side becomes a derivative. Okay, so let's multiply by mu of x. So you get mu of x y prime plus p of x mu of x y equal q of x. Okay, so the left hand side is a derivative of some function. If what? So notice that if, so this is mu times y prime, here I should have mu prime times mu so that I get a derivative on the right. So if d mu dx equal p of x mu of x, then we get that mu of x y prime, together that the ODE becomes mu of x y prime plus p of x mu of x, which is now mu prime of x. Again, I forgot to multiply the integrating factor to the left. Don't forget this. Mu prime of x y equal q of x mu of x. And now this is mu of x y, the whole thing prime, equal q of x mu of x. And now you integrate and proceed. Okay. But then, I still didn't get mu of x. So I know that mu of x solves the following ODE. So the integrating factor, so an integrating factor solves the ODE mu prime equal p of x mu. But now this is what? This is a linear homogeneous ODE, because this is mu prime minus p of x mu equal to 0, which I can solve as separable. So this is mu prime over mu, or antiderivative method, p of x. So log of absolute value of mu, well, this is log of absolute value of mu prime equal p of x. Now integrate, and you get mu of x equal a e to the integral p of x dx. And this is the integrating factors. Now you can choose a, so choose, you want one integrating factor. The whole point is to find y, not to find all the integrating factors. The point is to find all the solution y. So choose a to be equal to 1. We get, it's enough to find one integrating factor. We get an integrating factor, we get that mu of x equal e to the integral p of x dx is an integrating factor to the ODE. I will allow to use the formula of the integrating factor directly, but you are responsible also of the proof. Okay, you need to know what's going on, because sometimes there's no direct method and you need to use the same reason. So this is how in general I want you to solve it. Before this, I want you to be careful that that you need to write p of x is a multiple of y. Okay, so the multiple of y prime should be 1. If the multiple of y prime is like x squared, you have to start by dividing by x squared in order to use this formula, p of x dx. Okay, so example, solve xy prime minus 3y equal x5. So this is linear, order 1. Linear is y prime multiplied by a function of x, y multiplied by a function of x, which is a constant here, equal x5. Okay, it needs to be linear. So let's say x is positive. So I divide by x, I get y prime minus 3 over x y equal to x4. So this is p of x with minus 3 over x. So we multiply the ODE by integrating factor mu of x. By the way, even if x was not told you for you to be positive, it's still fine. Okay, you can still like do a scratch work, like assume it's positive and let's multiply and let's divide by x. So mu of x, integrate 5 mu of x equal e to the integral of p of x minus 3 over x dx. And it's equal e to the minus 3 log x. X is positive, so e to the log x minus 3. And this is equal x power minus 3, which is equal 1 over x cubed. So multiply by 1 over x cubed, you get 1 over x cubed y prime minus 3 over x4 y equal to x. Now the left hand side is the derivative of 1 over x cubed y. Okay, check. I mean, this is 1 over x cubed y prime plus the derivative of 1 over x cubed minus 3 over x4 y. So this is always mu y prime. And this is equal to x. Now integrate. You get 1 over x cubed y equal x squared over 2 plus a constant. Now multiply by x cubed, you get y equal x5 over 2 plus cx cubed. And this is your solution. Notice that this solution is valid for all x, not only for x positive. Fine? But notice the following. Notice that the ODE has infinitely many solutions. So this is a remark. Satisfying y of 0 equal to 0. Yes, for all constants c is 0. And the ODE has no solution satisfying y of 0 equal y sub 0 different than 0. Okay? And a unique solution satisfying y of x0 equal y0 with x0 different than 0, and this is by Picard theorem. What do I mean here? I mean Picard theorem because if you go back to your ODE, you can use Picard theorem for x away from 0 because you get y prime equals 3 over x y plus x4, and this will be your f of xy. And this is f of xy is continuous, so you have f of xy equals 3 over xy plus x4, and f sub y equals 3 over x, 3 over x. Okay? And these are both continuous in an interval containing x0 if x0 is different than 0. So you know that you have a unique solution, and it's clear that you have a unique solution. However, it's clear from here, because whatever you get x0, you can solve and you can find c. However, if x0 equal to 0, you cannot use Picard's theorem. And even you cannot use what you did here, you cannot divide by x and things, but you can, let's say, you have a solution that is true for all x different than 0, and you have everything is continuous, like the coefficient is continuous. So then this will imply that this, what you proved here to be a solution for all x different than 0, to be also a solution for x equal to 0, since this function is continuous and differentiable at x equal to 0. Although when I proceed with x different than 0. And you can see that if I y of 0 equal y0 different than 0, plug in x equal to 0, let's say I'm solving y of 0 equal to 1, plug in x equal to 0, you will get 1 equal to 0. Yes? However, all these functions for all c satisfy y of 0 equal to 0. This is why this has infinitely solution, this has no solution. In this case, I have a unique solution. Anyways, this was something to say just on a side. So another example, let's solve x plus 1 dy dx plus xy equal to 1. And I have y of e equal to 1. So this is linear. Again, this is a linear ODE. And you have y prime. So I write in standard form y prime plus 1 over x plus 1 y equal 1 over x times x plus 1. So we multiply. So this is p of x. So we multiply the ODE by p of x by an integrating factor mu of x equal e to the integral p of x dx, which is equal e to the integral of 1 over x plus 1 dx, which is equal e to the log of absolute value of x plus 1 equal absolute value of x plus 1, but x is close to e, so this is equal, so this is positive, but it's inside, so this is x plus 1 for x close to e. Now multiply by x plus 1, what do you get? We get x plus 1 y prime plus y equal 1 over x. Now notice that the left hand side is the derivative of mu, which is x plus 1 times y, the whole thing prime. I mean, the derivative of x plus 1 times y is x plus 1 y prime plus the derivative of x plus 1, which is 1 times y, equal 1 over x. And now you integrate, and you get x plus 1 y equal log of x. Remember, x is positive, so solving near x equal to e, plus a constant, so y equal log x over x plus 1 plus c over x plus 1. Okay. And this is your solution. No, we still have the initial condition. I have y of e equal to 1. So replace, I have got log of e over e plus 1 plus c over e plus 1 equal to 1. This implies that c 1 plus c over e plus 1 equal to 1, implying that c is equal to e. So y of x equal log of x plus e over x plus 1. And this is now your solution to the initial value problem. Okay, some modeling now. So recall the free fall problem. Okay, the free fall problem, I had the following equation. I had an object that is falling, and then the ODE was m v prime minus m plus gamma, sorry, it was m v prime plus gamma v is equal to mg, correct? And this was your ODE free fall. Now this is linear, and we gave it a graphical solution. If you remember, we took let g be equal to 10 and assume gamma over m is equal to 1 over 5. And then we took the equation v prime, so the ODE became v prime plus 1 over 5 v is equal to 10. Now how do I solve it? I multiply, so this is linear, multiply by e to the, by the integrating factor mu of x equal e to the 1 over 5 dx, and it's equal e to the x over 5. Then I get e to the x over 5 plus 1 over 5, well, y prime, plus 1 over 5, v prime, sorry, plus 1 over 5 e to the x over 5 v equal 10 e to the x over 5. Now the right hand side is, it's, okay, sorry. So this is time. Here v was a function of t, so all these are t, not x. So this is e to t over 5 v, the whole thing prime, equal 10 e to the t over 5. Now integrate, you get e to the t over 5 v equal, well, the integral of 10 e to the t over 5, so this will be 50 e to the t over 5 plus a constant, and then this gives me v equal 50 plus c e to the minus t over 5. Okay. Now notice the following. Notice that as t goes to infinity, what happened? So what is the limit as t goes to positive infinity of v of t? This is equal to 50. This was the equilibrium solution. So here your solution is written as a sum of two terms. One term is going to 0, another term that survives after t goes to infinity. So here's the second term goes to 0 as t goes to infinity. It's called transient term. Okay. Now all remaining term, the remaining term as t goes to infinity, which is here 50, is called the steady part of the ODE, which of the solution, which is a part of the solution that will matter for t very large. Okay. We already did this in many, well, we already did this graphically when we started in the free fall model. And then there's more models which come from circuits, so model from electric circuit. This you can find them in 3.1. If I have a, let's say I have a generator E, and I have a coil, and then I have a resistance. So the inductance is L, this is voltage. This is called an LR, well, LR or RL. LR circuit or RL circuit doesn't matter. And you have an RC circuit, which is a generator E, and here you have a capacitor, it's capacitance C, and here you have a resistor R, and this is called an RC circuit. Well, I'll give you the ODE of both of these two equations. You can see obviously that they are linear. So in the first equation, if you add the voltage, you have E of t equals the voltage in the coil. Now you know that the coil, you should know that the coil, create a magnetic field, and then the current is, the voltage, it creates a voltage when there's a change in the current, because the change in the current create a change in the magnetic field inside the coil. So this is L di dt, and then there is a voltage across the coil, and then plus Ri, and this is the voltage across the resistor. This is Ohm's law. Okay. Now what about here? You have here ET. This is for RR circuit. You can see this is obviously a linear ODE. Here you have ET is equal to the voltage across the capacitor. So the voltage across the capacitor is 1 over C times Q, where Q is the charge of the capacitor. And then plus Ri. Now you have Q and I, but dQ dt, I is equal to dQ dt. So this implies that E of t equal 1 over C Q plus R dQ dt. And you can solve this ODE. Now let's do it. Assume an RC circuit, and I'm trying to charge a capacitor. We have E of t is equal just a constant E sub 0. Let's solve it. How would be my equation? So it will be R dq dt plus 1 over C Q equal E sub 0. Now this is linear. So you get dq dt plus 1 over RC Q equal E0 over R. Now multiply by mu of t equal e to the integral of 1 over RC dt. And this is equal, well, this is a constant, so this is e to 1 over RC t. So you get e to the 1 over RC t plus 1 over RC e to the 1 over RC t Q equal E0 over R times e to the 1 over RC t. And now this is e to the 1 over RC t. Here you have Q prime times Q, the whole thing prime, is equal e to 0 over R e 1 over RC t. Okay, now we integrate. And you get e to the 1 over RC t Q equal E0 over R times R, well, as the integral of e to the AX is equal to e to the AX over A. So e to the, so RC times e to the 1 over RC t plus some constant. I will call it A because I have already my C. So this is a constant. So this gives me that Q is E0 over, well, no, Q is, the R will cancel. So this will be E0 E0 times C plus A e to the minus 1 over RC t. Now this is a transient term, and this is a steady because this goes to 0 as t goes to infinity, and this is a steady state term. Okay, let me check just the calculation. So this is e to the 1 over RC E0 over R. Yes, 1 over RCT. So this is e to the 1 over RCTQ equal E0. Now you have to integrate, so this is still the same. Now this is RC e to the 1 over RCT because, I mean, because e to the AX is the AX over A, and A here is 1 over RC. Now the R will cancel, so you get E0C E0 times C into 1 e to the 1 over RC plus T, and this is steady state term A e to the minus RCT, and then you get your solution. Okay, so I will stop here with the models. By the way, we finished section 3.1 now with all the models that we did for, we did many models. We did the bacterial, the growth model with the radioactive model. We did the Newton's law of cooling and warming, and we did the circuit in series for RL and RC circuit. This is in section 3.1. There's many models, by the way, and this can come as an exercise, and then the whole point is that you have to solve the ODE and know what it means. Okay, thank you.